Hello, this is Rick from MathX, and this is part 3 of our little series in which we find out all the different ways to compute for the area of a triangle. Today we're going to be using a method which I like to refer to as SAS. And even though this is not the formal name for this method, as most people who use this method typically just remember by the equation, this is what I'll be referring to it as, to make it simple. So let's take a look at the equation. The equation is like this. A is equal to 1/2 AB sine C, where A is the area, C is an angle, A is an adjacent side, and B is an adjacent side. And the thing about this method, compared to all the other methods we've used to compute for the area of a triangle, is this method involves an angle. And the sides that are also in this method are in a specific relationship to this angle. In this figure to the right, we have an example of a triangle which you could use this SAS area method on. And we can see how the sides A and B relate to this angle C. In order to use this formula, we have to make sure that A and B make up the sides of angle C. And this is the only way we can use the formula. We can't plug in the values C and B and then multiply that by sine C. No. The sides A and B must be the adjacent sides of the angle C. And that's the only case in which we can use this formula to find the area. That's why I like to refer to it as SAS, because it matches the SAS congruency pattern. Side, angle, side, in that exact order. Just as to find the area, we have to multiply side with the sine of this angle with the other side, and then take half of that. So this is the first formula that I've shown you in which angle plays an important part in finding out the area. Now, in this figure, we've discussed a lot of the terms already. We've discussed how A and B both have to be sides of the angle that we find the sine of. But I haven't really discussed what sine even means. And for those of you who do not know basic trig, sine is just the ratio in a right triangle between the opposite side and the hypotenuse. So the sine theta of the angle shown below would be this opposite side divided by this hypotenuse. So for everyone who's taken trig, they're probably thinking, okay, so this is only applicable when I have a calculator. Well, the thing is, this is applicable even if you don't even know any trig, if you just know some geometry. Because we already know the signs of some angles already. In the cases of two triangles, like this 30-60-90 triangle, and this 45-45-90 triangle, these are both right triangles. So if we take the sine of each of these angles, like the sine of 30, we would just do the opposite side to this angle divided by the hypotenuse. So in this case, if we try to find the sine of 30, we would do A divided by 2A, which would give us 1/2. So thus, sine of 30 was 1/2. Similarly, if we try to find sine of 60, we're going to take the opposite side. We're going to divide 2A from that. So it'd be A root 3 over 2A, which would give us root 3 over 2. And just like that, sine 60 is root 3 over 2. Same thing we could do with this 45 angle here. If we want to take sine of this 45, we would take the opposite, which is 1, and divide it by root 2. So sine of 45 is 1 over root 2. Now what if we want to take a sine of this 90-degree angle? Well, in the case of a right triangle, the side opposite to the 90-degree angle is the hypotenuse. So if we divide the opposite side by the hypotenuse, since they are the same side, the sine of this angle would be 1. So sine 90 is equal to 1. So just like that, just from a couple triangles, 30-60-90s and 45-45-90s, just some of the triangles we already know. We can already compute some sides, showing how even though this method for finding area involves some trig, you don't really need to know that much trig in order to use it. So here's a table of all the signs we already know. So let's try this method out on an example problem. In this case, our example problem is number 14 from the AMC 10B of 2005. And it states that equilateral triangle ABC has a side length of 2, with M being the midpoint of AC and C being the midpoint of BD. And it's asking for what the area of CDM is. Okay, so we want to find out what the area of this triangle CDM is, right? So if we figure out what this angle is and how to find the sine of this angle, multiply it by this side length and this side length. Because remember, finding area using SAS can only occur if it's side angle side in that exact sequence. And then divide that result by 2, we're going to get the area of this triangle. So let's try that out. It tells us in the problem that M is the midpoint of AC. And since we know it's an equilateral triangle with a side length of 2, that would mean that MC is equal to 1 as stated here. It also tells us that C is the midpoint of BD. So if it's a midpoint, that means that BC and CD have equal lengths. So if BC is 2, CD is also 2. So we already know 2 of the side lengths. Now we just need to figure out the angle, MCD. Well, the thing is, since triangle ABC is equilateral, all of its angles are equal. So each of them are 60. But we see that ACB and MCD form a straight angle with length of 180. So if ACB is 60, MCD is 180 minus 60, which is 120. So in order to compute for the area of triangle MCD, we would multiply 1 times 2 times sine 120 and then divide that by 2. But here's the thing. In our chart of sines, you'll see that we didn't really have a value for sine 120. But there's no need to fret about that, because here's the thing. Sine 120 is equal to sine 60. And we can take a look at that, try to analyze why that is. In this case, if we drop an altitude from here to here, we'll see that sine 60 is equal to this opposite height over the hypotenuse. But that's pretty obvious. However, if we take 120 from here, and we still look in that kind of respect, the height will still stay the same. And technically, this is still the hypotenuse. So the opposite over the hypotenuse would still be the same. That's why we get sine 120 is equal to sine 60. Now we know the value of sine 60, so we can just write an equation and just compute for the equation. So plugging in all the values we know MC is 1, CD is 2, and we know we have a sine 120, which we can later substitute with a sine 60. And as we know from the previous chart, sine 60 is equal to root 3 over 2. So the area of this triangle will be 1/2 times 1 times 2 times root 3 over 2, which is simply root 3 over 2, because the 2 and the root 3 over 2 would cancel out to give us root 3, and then root 3 times 1/2 would give us root 3 over 2. And ultimately, we would get an answer of C. So as you can see, we used an interesting method to solve this mid-tier AMC 10 problem. Even though this method had a little bit of trig in it, the amount of trig needed to properly utilize this method was still not unbearable, as we already know a couple of sine values already. So using this method, you can find the area of any triangle if you just know 2 of its side lengths and the angles sandwiched in between them. If you have a calculator, you can do this with any triangle, as long as you know the side lengths and the angle sandwiched in between them. But even if you don't have a calculator, there's still some sine values we already know from experience, such as the sines of the angles inside of 30, 60, 90 triangle, and the sides of the angles inside of 45, 45, 90 triangle. So that just makes finding areas of these such triangles much, much easier. And even if we don't have a sine that we already know, we can always use some logic to relate it to a sine we already do know, to make solving the problem much easier. So next time you see a problem in which you have to compute the area of a triangle, where you only have two sides and the angles sandwiched in between them, remember to use this formula. And this is just one of another great tool to use in competition maths. Anyways, up until this point, we've only been using sides and angles of the triangle. But in the next video, we're going to use a different property of the triangle to compute for its area. In the next video, we're going to be checking out how to utilize the in radius to find the area of the triangle that the circle is inscribed in. And I'll be showing you how you can use this to solve some high-tier problems on some interesting competitions. So tune in next time to learn that.